Hello everybody and welcome back to the 2003 Hypatia. We're on to the last question, question number 4. Okay, so the Friar Galois Hypatias, they only have 4 questions. So question number 4, we're on the last one. I will remind you that even though this is the year 2003 and there are extensions to the problems, I will not be going through the extensions. So this really is the last question. If you're looking for more Hypatias, I'll be uploading more soon. We're going to go on to the 2004 in the next set of videos. So, we're on to question number 4. Let's take a look. Alright. Square ABCD has vertices 1, 4, 5, 4, 5, 8, and 1, 8. So that's square ABCD, and we can see each side is going to have a side length of 4. Okay. From a point P outside the square, a vertex of the square is said to be visible if it can be connected to P by a straight line that does not pass through the square. So for this P right here, we can see A and B, but if we were to connect P to C, we would go through the square. So it's a straight line that does not pass through the square. Okay. So, thus, from any point P outside the square, either 2 or 3 of the vertices of the square are visible. Okay, you can have down here, this P, only A and B are visible. But if we moved it off to the side, sort of below maybe the X, we'd be able to see A, B, and C. Okay. The visible area of P is the area of the one triangle, or the sum of the areas of 2 triangles, formed by joining P to the 2 or 3 vertices visible on the square. So here we have P, and we can see A and B. We've connected A, B, and P. That's a single triangle. And I imagine in one of the later ones, yeah, here we go. This Q, it can see A, B, and C. So we have 2 triangles, and that gives us the visible area there. Okay. Show that the visible area of P at points 2 and point 2, negative 6 is 20 square units. Okay, that shouldn't be that hard. We've got a single triangle. It's not that hard to see this is going to, the line AB is going to be a base. So if we can just figure out the height, we should be all set. So we'll draw ourselves a little bit of the picture. So here's A, here's B. I don't really care about C and D, but they are up here. And we have a point P, and it's somewhere down here. And it's at 2, negative 6. B was 5, 4. And A was 1, 4, if I recall correctly. And we'll draw the triangle in orange. So that's the area that we want to show happens to be 20. So it's clear from the coordinates that A, B, C, D has side length 4. I don't think we really need to go into that. You just sort of take the difference in the x coordinates. I mean, noting this is at best a mark, but I don't even think that would be worth a mark. Okay, these questions are out of 10, so I have to figure it's probably something like 2, 3, and 5, or 2, 4, and 4, or maybe 3, 3, and 4, something like that. And we have a little more to do than just figure out side length here. Okay. So let's just double check that we have the coordinates correct. So it's 2, negative 6, 1, 4, and 5, 4 are the ones we care about. Okay. So we can, using the dark purple, drop a perpendicular from P to a new point E, and that will be at 2, 4. So this is going to make PE an altitude. Or a height, and we're going to have a base in this case of AB equals 4. Okay? So we have a base, and now our height. So the length of PE is the difference in the y coordinates. And so it's 4 minus negative 6. And we take the absolute value. You can't have a negative height. So we just throw absolute value bars around it. And we'll get an absolute value of 10. Okay. So triangle TAB, the area is going to be 1/2 base times height. Which is a formula we encounter oh so often on these contests. And the base is 4, and the height is 10. And we're going to get 20 as desired. So we've shown it that it is 20, and we've explained our reasoning. We defined a base and a height. We calculated the lengths of both of those. The area of the triangle formula takes care of the rest. Okay? So that's A part. B part, we already snuck ahead and looked at it. And it involves a new point Q, where the visible area is the sum of two triangles. And what is B asking us? Show that the visible area, so the area that is the sum of these two triangles, of Q at 11, 0, so it's going to lie just on the x-axis, is also 20 square units. Okay. So in this case, we're going to have to figure out some way to calculate the visible area. Now, it's already cut into two triangles. And so if you've tried this question already, you might think, well, if I have to figure out the area that happens to be the sum of two triangles, why don't I figure out the area of each of those two individual triangles? And that's the way we're going to handle this. So we'll draw ourselves the picture. This time we'll have the point Q in there. You bring a ruler to your test, you might get a better picture than I usually draw. But as long as we can understand what's going on in our picture, it doesn't really matter. A, B, C. And we'll use orange again. Actually, we'll use orange for one triangle, and we'll use pink for the other triangle. So the visible area is equal to triangle QAB plus triangle QBC. So let's figure out each of those individual areas. Okay. Now for both of them, we have a base of 4. Right? It's a square. And we already commented that we have a side length of 4, so AB can be a base with 4 for the first triangle, and BC can be a base of 4 for the second triangle. Okay? So for our first triangle, we can drop an altitude Okay, and we can call this point E. And for our second triangle, we can extend it a little bit and say, well, from Q down to our extended BC, where do we get our intersection point? Where do we get our altitude? We'll call that point F. F will be at 5, 0, and E will be at 11, 4. Okay. So we'll just explain what we did a little bit. So we extend bases AB and BC. We can find E, and E was 11, 4. And F was 5, 0. We can find E and F respectively. So QE and QF are respective heights or altitudes. Okay? So using these, we find the areas of the triangles. Okay? So triangle QAB, that's going to be 1/2 base times height. And that's going to be 1/2 AB times QE. And that's 1/2 4 times, well, what's the height of QE? It's going to be the difference in the y coordinates again. It's going to be 4 minus 0. And this is going to work out to be 8. 1/2 of 4 times 4. So that's 1/2 of 16. That's going to be 8. Okay? And we can also figure out QBC. Now, one thing to note, how do we know how to compute these heights? I would say it's clear from our diagram. And since AB, BC, these are parallel to the x's and y axes, it's clear how to find E and F. They're going to have identical x coordinates or y coordinates depending on the direction, and so the height becomes very clear: difference in y coordinates or difference in x coordinates. But if you need to, by all means, give an explanation. If you're unsure, if you think you're making even the slightest bit of leap, stop, think about it, and write out an explanation. You have to balance obviousness of a picture versus explanation, because it's the explanation that gets you the marks. So don't give a 2-page explanation as to why difference in y coordinates gives us the length here. I mean, if you really, really want to, use a distance formula or something like that, but I would say that's overkill. It's not about whether or not we can recognize perpendicular lines and lines parallel to the axes, and whether or not we can rigorously prove that there's a really quick way to figure out the length of such lines. It's about, can you figure out an altitude? Can you figure out a height? Can you figure out a way to calculate the area of these triangles and add them up? Okay? It's not life or death math proof. It's not a research publication where you have to absolutely have all your bases covered. You have to be able to judge whether or not this needs to be in there versus this needs to be in there. And I would say picture is worth enough. It's clear. If you can say these are definitely the coordinates, you don't need to explain where you're getting the height from. Just give the absolute value as we did here. Okay? So for those of you who are worried about that, so here base is going to be BC times QF, and it's going to be 1/2. Once again, the base is 4, and we're going to have 5 minus 11, so that's 1/2, 4 times 6, and that's going to be 12. Visible area, well, that's QAB plus QBC, and we just showed that those are 8 and 12 respectively, and it's 20. So we've done the work, we explained where we're getting these altitudes from and the coordinates they have, which makes our calculations much simpler, and we've got a value of 20. Okay, and that's B part. So we just have one more part to go, and then we're done the 2003 paper, even though we can see these extensions here. So, C. The set of points P for which the visible area equals 20. Okay, so for example, this P is in this set, and this Q is in this set. So where the visible area equals 20 square units is called the 2020 set. Okay, and is a polygon. All right. Determine the perimeter of the 2020 set. All right. So how might we go about figuring this out? Well, we've done some interesting work about this, and we were introduced to the idea of being visible and visible area. And I would suggest that if you're stumped, you go back and reread the paragraph that describes what is visible and visible area. Okay? Now, the things I pick out of this paragraph are the following, that from any point P outside the square, either 2 or 3 of the vertices of the square are visible. Okay, so we have two cases. Either it's something like this P, where we have a single triangle, and it's got to have area of 20, or we have something like we just saw with B, and at this point Q, where 3 of the points of the 3 of the corners of the square are visible, and we have to sum up the area of 2 triangles and get 20. So what we can do is we can say, okay, what are all the points that give me 2 visible points on the square? And so I'm just calculating a single triangle's area. What are all those points? And then what are the other points, the points that require 2 triangles to make up an area of 20? Okay? So let's stop and think about those for a second. All right? So all the points that just see 2 of the corners, it's going to be something like, well, can they see A and B? Can they see A and D? Can they see D and C? Can they see C and B? Okay? And something like point P can see A and B. And if we wiggle him around a little bit, if we move him to the left or to the right, he's still only going to be able to see A and B. It's not until he sort of lies on the line BC and moves past it that he might be able to see C. Right? He can be directly in line with B and C, but B is in front of him, so he can't see the C behind him. Right? So as long as we move P around just a little bit, it's still going to only be able to see A and B. Okay? So we know that around this particular P, we get other values that just see 2 vertices. If we go too far, if we go past the extended line CB or DA, we'll be able to see another vertex. Okay, and so then that's a completely different case. All right. So let's get a completely fresh piece of paper. So which points in our 2020 set can see 2 corners and which can see 3. Alright, I'm going to drop the axes for a moment. We're just going to put this square ABC here. ABCD. Now we've already seen a point P down here. And we've seen another point Q out here who can see 3, and P can see 2. Now, for a second, try and think about ways that we can wiggle P around and still be able to see AB. Okay? Are we going to be moving around on an arc, on a circle, or are we going to be moving in a straight line, or some weird other structure? So think about that for just a second. Okay, now think about ways that we could move Q around. Okay, now we're going to tackle the case with P first. So no matter what, with one triangle, A and B, we're going to have a base of 4. Okay. So points that can see 2 corners form a triangle with those corners. And they have a side of the square as a base. This is exactly what we saw in A part. Okay? So we'll always have a base of 4. To get area of 20, stop and think. What do we need? We know we have a base of 4, and we're looking at a triangle, so what else do we need, and what else is fixed? Right, if we have a base of 4, the only thing that's left to determine the area of this triangle is the height. And the height must be constant, because the 4 is given. We're going to have a height of 10, just like we did in A part with that original point, P. Okay? So any point which can see 2 corners and is 10 units, I guess, away from the square is in our 20/20 set. Okay? So that's going to be all these points out here and above here and over here and down here. They're going to have a length of 4. And we'll use green again. And they're basically just going to be the sides of the square, and we've extended them out. We've sort of ripped them away from the rest of the square. So these blue lines here that are bound by our extensions of the line AB, the line BC, the line CD, and the line AD. Okay? So we notice that the point P, he sits about here, and he's exactly where we need him to be. And if we shuffled P along a little bit, on the same line, we'd still have a height of 10, although the point where our altitude hits the base will move as well. We'll still get a distance of 10. And if we keep moving P to the right, eventually we'll cross this line here, the extension of B and C. And then at that point, we get into a range where we can see A, B, and we can just barely see C, and as we keep moving, we'll see more of A, B, and C. All right, and by symmetry, we're going to have the exact same argument. Squares look the same on all sides, so we're going to get these places as well. Okay. So there's one other case, and that's the case of Q, which is sitting about here, I guess. And Q can see 3, can see A, B, and C. Okay? So that leaves us with the points that can see 3 corners. Okay? And hopefully you did my little verbal exercise before. Think, how can we move Q around and still get a visible area of 20? Okay, so think about that again for a second. Can we move Q around at all? Or is Q sort of fixed there and then there'll be another point somewhere else up here, somewhere else down here? Well, the question at least tells us that we're looking at a polygon, and the simplest polygon would probably just connect up the blue areas into a very symmetrical but still kind of stretched octagon, and Q would lie on the line between sort of the BC and the AB lines here. Okay. Now it turns out this is the case, but can we make an argument that would suggest that? Okay. So for points like that, for such points, the visible area is the sum of 2 triangles. Right? This is the other case. Before it was 1 triangle, now we're adding up 2 triangles, just like in part B. And each of these triangles have a side of the square as a base. Okay, so for Q, it's AB and BC. For a point sort of in the first quadrant relative to the square, it would be base of DC and BC. Okay, for a point opposite of Q, we'd be looking at 2 triangles, one of them having a base of AD, one of them having a base of DC. So these are 2 triangles with bases equal to 4. So let's just put in dummy variables. Let's let x and y be their heights. Visible area is going to be 1/2 4 times x plus 1/2 4 times y. And that's going to work out to 2x plus y. If we want the visible area to be 20, we need their heights to add up to 10. And that's very similar to the case we had with p. There we had a single height that had to be 10, but now with a point like q, we have two different heights, and they have to add up to 10. Okay? Now this looks awfully suspicious. It's almost like a standard form equation of a line, and you'd be correct. X plus y equals 10. Standard form of a line is ax plus by equals c. So this is very suspicious indeed. And it turns out we get exactly what we want. These heights are going to lie on a line. Okay? So I put our A, B, C, D in here. Now the points Q don't lie on the line x plus y equals 10, but the idea that the heights are so related suggests to us that we should be looking for a line. So we'll put in our blue points, our points that can only see two corners of the triangle. Just redraw our picture a little bit. What we're going to have is a line like this. Now how can we prove that it's a line? Okay, so suppose R can see A, B, and C. So we'll put R up here, very close to Q. And we'll add in our green dotted lines of height 10. So one height is x and another height is y. And here are our orange triangles. So very colorful, very festive looking diagram. Someday maybe I'll draw a diagram that'll have enough that it'll have rainbows in it. And we'll have the points E and F. So to find these new points E and F, very similar to B part when we were talking about Q. For some reason today I keep forgetting the E in height, so I apologize for that. Alright, so we have X and we have Y. We know X plus Y equals 10. Oops. So really, we can get rid of this Y and just say RF is 10 minus X. Okay? So F lies on the extension of BC, and that's the line X equals 5. Alright, just go back and double check the coordinates. BC both have an X coordinate of 5, so they both lie on the line X equals 5. And E lies on the extension of AB, and that's the line y equals 4. Okay? So R R will have coordinates. Now, how do I want to say this? Let's figure out the coordinates of E and F first. So F will have an x coordinate of 5 and a y coordinate of, well, it'll be below 4 by x amount. So 4 minus x. And E will have coordinates, well, it lies on the line y equals 4. And from B, we go over y, which is 10 minus x units. So 5 plus 10 minus x. Okay? Now we subtract off of 4 because r is sort of down and to the right. And we add on the 10 plus x because r clearly has an x coordinate greater than. So we add on the length there, as opposed to subtracting it when we figure out f, which is below. Okay. So this tells us if we combine the coordinates, r is going to have x coordinate 5 plus 10 minus x, and y coordinate r minus x. So r is really at 15 minus x, 4 minus x. Let's just double check. I'm just wondering why we have a minus 2 minus x's here. 4 minus x, yeah, that should be fine. Okay. And so this is on the line y equals x minus 11. So if we went the other way, we'd get other lines. So the other red lines, which we could draw in. And I can't figure those out in my head. I encourage someone to leave them in the comments if they're really interested. So the lines, the points in the 2020 set which can see A, B, and C must lie on this line. Okay? This gives us a line when we can see A, B, and C, but there's no reason we couldn't carry out this exact same analysis when we're looking at B, C, and D, or C, D, and A, or D, A, and B. So our 2020 set is an octagon, just as we've been drawing and just as we predicted a while ago. So we have our square in the middle, and we have each of these, which is length 4, and they are 10 units out. From the square on either side, and lines fill in the rest. These lines are parallel to y equals x and y equals negative x respectively. For example, we have worked out one of the lines right over here. So that's this line in the bottom right. Okay. But we're not asked what shape is it. We are asked to prove what is the area. So we have 4 4s. And inside each of these is going to be 10. Each one of these blue lines is distance 10 away from the square. We want the perimeter of the 2020 set. So it's 4 copies of 4. Plus 4 copies of the hypotenuse of each of these right-angled triangles here. With side length 10. Okay. So that's 16 plus 4 times the square root. We just used Pythagoras theorem. 10 squared plus 10 squared. That should give us, so the sum of the side lengths squared, sum of the squares of the side lengths is equal to the square of the hypotenuse. So to find the length of the hypotenuse, we just take the square root here. And we get 16 plus 4, square root of 100 plus 100, that's 200. Okay. So that's 16 plus, we can take out a factor of 100 here. We have 4 times 10 root 2. So 16 plus 40 root 2. And if we were to grab our calculator and just work that out, we would get a number that is about 72.5. Okay, but we leave it in exact form. If you were to, you can give the decimal, but that shouldn't be your final answer. I think there was a 6 there as well. We want to leave things in as exact an answer as possible. This is a good idea for us for 2 reasons. One, you give the most exact answer possible, there's no way they can say, sorry, this isn't close enough. You give the actual exact answer. There's no closer you can possibly get. And if we look and see, oh, there's a D part, or maybe for this contest, oh, look, the extensions build on this previous question. If you need to come back and work with this value, you want the exact one written out, because the second you start putting in rounded values, you get an even more rounded value as the answer. It's even further away, and eventually your rounded calculations can start shifting you away from the actual exact answer by quite a bit. Okay, so always leave your answers as exact as possible. If they ask for 2 decimal places, give that, but make sure somewhere else in a box you do have the exact answer. If not for them, but maybe for you later on in a later calculation in a subsequent part or a subsequent question. Okay? So 16 plus 40 root 2, that's the perimeter of our 2020 set. I think that was a nice little question. And I believe the extension does sort of a 2020 set, but for a cube, which is quite interesting. But as I say, I'm not going to go through those unless there's a high enough demand. But that does it for the 2003 Hypatia. The very first Hypatia got us used to the contest and the proof-based concept. So I think that's very nice. And that about does it. So join me for another Friar, Galois, maybe the 2004 Hypatia even, or just another video on my channel, and I'll see you guys